All right, so before the break, we were taking a look at how do you compute the partial of the loss with respect to one of the weights. And if there are multiple paths involved in going from the loss to whatever weight, for example, in this case, we were taking a look at W12, right? So as you saw, there's a red path involved over here. So all the chain of partials in this path will be involved. And then there's another blue path over here, which also will take us to the same weight, starting from the loss. So there will be another chain of partials, which will be then added to the previous chain of partials to compute the entire answer over here, right? So, anyway, so there's a plus over here. This part over here is the total answer, and this was just the answer for the first part. This was just the answer for the first part. The total answer, as you can see, is this plus whatever is at the bottom, right? Okay, and as we discussed before the break, if we have a more complicated, more involved network, there could be hundreds of paths going from the loss to a particular weight. So, you know, sitting and computing all these partials yourself, you'll go crazy. Okay, so is there a more easier, simplistic way to come up with that answer, right? So now I will introduce a very compact formula or algorithm for computing the partials of the loss with respect to the weight, and this is called the delta rule. Okay, so we will abbreviate it like the Greek letter delta. Okay, so the idea is like this. In the delta rule, what we do is we work backwards, right? And by the way, delta is basically defined as the derivative or chain of derivatives from the loss up to the middle of the neuron. So if you can remember this important property, everything else will be easy. Okay, so think of this. See, this is the middle of the neuron, right? Whatever is the chain of derivatives from the loss up to the middle, meaning up to S1 of 2, will be the delta for that particular neuron, right? Very similarly, there will be a delta over here. There will be a delta over here. There will be a delta over here. Following our terminology, what would you call this delta to be? One of one, layer 1, right? What would you call this?
2 of 1.
2 of 1. Very similarly, let's go over here.
Delta 1 of 2.
1 of 2 and 2 of 2. Okay, so by the definition of the delta, like I said, it is the derivative from the loss up to this point. So what's the definition of delta? Okay, delta 1 of 2 is essentially partial loss over partial S1 of 2, right? You guys agree? From here to the middle of the neuron, which is what? Partial L over partial, which is equal to partial L over partial A1 of 2 times partial A1 of 2 over partial S1 of 2. Right? So do we know this well? What will be partial L over partial A1 of 2? Okay, won't this be 2A1 of 2 minus Y1? Everybody agrees?
Yes.
right? Times partial A1 over A1 of 2 over S1 of 2. So what's involved over here? Sigmoid, so what will be the answer?
A1, 1 minus A1.
A1,
A1, 2.
2.
So we know delta 1 of 2. Right? Very similarly, let's find delta 1, delta 2 of 2. Okay, so once again, by the definition of the delta, it's the derivative from the loss up to the middle of the neuron, right? So this will be what? Partial L over partial S2 of 2. Everybody agrees? Take a look at from the picture from here to the middle of the neuron, right? Okay, so what will this be equal to? Partial L over partial A2 of 2 times partial A2 of 2 divided by partial S2 of 2. What will this be equal to?
2, A2, 2 minus Y2.
Times 2, 1 minus. Everybody agrees? Okay, so now here's the interesting part. Were there too many partials involved in computing these deltas over here?
No.
It was just two partials, right? So not too bad. So now the interesting part is that the deltas over here can be computed in terms of the deltas over here, based on what's connected to them. Great. So for example, let's take a look at delta 1 of 1 now, and see if we can express it in terms of these two deltas. Okay, so if you take a look at, let's first get to this point over here, to where I put the dot over here. Would delta of 2 of 2 come over here, right?
Yes.
And it will come through here through which way?
A1.
I mean, A1.
The weight 2, 1, 2.
From here, which weight is involved to get us to this point?
The weight 2, 1 of 2.
W21 of 2, right?
Yeah.
So if we multiply delta, this delta was called 2 of 2, right? Delta 2 of 2 multiplied by W21 of 2. So that will be the contribution of this delta in this blue path over here. What will be the contribution of this delta to this point?
It's weighted by W1, 1 of 2.
It is weighted by, so this will be W1 of 2 over here, weighted by W11 of 2. Right? So now what will this delta be? Further, it will get multiplied by, remember it's going through, there's another partial involved.
Yes. A11, 1 minus
A11, 1 minus A11.
Yep.
So, as you can see, very easy to compute.
That's the.
So that will be delta 1 of 1. Can we also now compute delta 2 of 1?
Yes.
Okay, see, first give me the expression in terms of these deltas.
This is delta 1 of 2
Delta 1 of 2
weighted by
Weighted
1
by-
of 2.
Okay, then plus
Delta 2 of 2 weighted by
weighted by W2 of 2, correct? And so this will give us up to this point.
And we need to do the
Further, we have to pass it through the activation.
Yes.
So this will be
A21,
A21,
1 minus
1 minus A2.
A21. Yep.
So this will be the expression from this one.
That's
Okay, as a homework now, okay, wait, we're not done yet. So we know all the deltas over here, correct? So now can you tell me, for example, what will be the value of partial L over partial W21? Just like we did before. Sorry, we were doing 1, 2, not 2, 1.
Delta 101.
Delta 101, very good. Then what else?
And then we need to weight it by x2 then.
Exactly.
And then we do plus delta 201.
No, that's the only
Oh
one.
yeah, that's the only part. Yeah.
Because this is only this delta is involved.
Yes, yes.
Okay. So anyway, the neat thing is, as you can see, as we work backwards, right? The deltas are easy because there's only 2 partials involved to come to the last layer. The deltas in the last layer, right? Then these deltas, as you can see, were simply the weight multiplication of these deltas. Further, of course, activation was also involved. And then once we are at the very first layer, then whichever previous input connects to it, for example, let me see if you can tell me right away now. If I asked you what will be partial L over partial W22 of 1? Delta 2 of 1, right?
Yeah,
Times x2.
times x.
In times x2. Okay, now the question is, coming back over here, for example, this part over here, it has to be 100% same as this, right? The sum of this long chain, sum of this long chain. So I will leave it as a homework. One time you should expand it out, all the deltas, and convince yourself that this indeed is 100% the same. Otherwise, it will be a wrong answer, right? Okay, so to summarize, this is how we train deep neural networks. Okay, in deep neural networks, okay, in deep neural networks, there will be many, many layers of neurons involved. So this could be one layer. Okay, then this will go right? Then there will be another set of weights, W's over here, W's over here. Then there will be another okay, so anyway, and so on and so on. So the X's will go over here, feed into all the neurons. Then these neurons will, through the weights, will go to the next layer, through another set of weights will go to the next layer. We keep going until we produce actual outputs over here. Then basically through the expected Y's, we will pass it through a loss function. And we'll find the loss, and then we'll work backwards to compute the partial L with respect to all the W's. Yes?
He actually concluded the universal approximation theorem by stating one hidden layer is more than enough.
As we discussed, even though from classification point of view, one hidden layer is enough, right? So why would we want to use more than one hidden layer? The two layers sometimes will be more efficient in terms of the total number of neurons needed, because it will still do the same job as a one hidden layer, but you may need a lot of neurons in that hidden layer to get the equivalent. Second thing, as I hinted to you guys, and it will become more clear as we go along, is from a classification point of view, meaning from a decision boundary creation point of view, sure, we don't need more than one hidden layer. But what if the first layer is doing some special transformation to a new high dimensional space, which will help us later in the classification? So from that point of view, we do need more layers. Okay, so anyway, so let's summarize our approach, our general approach. For us to be able to compute partial L over any partial W, regardless it's here or here or here, there will be weights involved over here. What will be our general approach? As you guys saw from the last example, what will we do first? Compute deltas where?
In the middle of the layers.
In the last layer.
Yes.
So compute the deltas over here.
Yeah.
Okay, so then from these deltas, we'll compute these deltas over here. Correct? And what was the relationship of this delta with respect to this delta?
They're weighted by the weights that connect the neurons.
Whatever weights was connecting, right?
Yeah.
Now, can you guess if I have hundreds of neurons? So let me give you an example. Suppose I have 100 neurons here. Suppose I have 50 neurons here. How many weights will there be involved? Because remember, each neuron goes to all the 100.
150.
So won't it be 50 times 100
Yes.
weights?
The Cartesian.
Can we put them in matrix form?
Yes.
Yes.
Right? And so this is what we'll do very soon. Everything will be in matrix form. Okay, if it is in matrix form, now let me ask you, can you guys guess? How will we compute these deltas from these deltas?
So just take the product.
Is this a matrix or is this a vector? See, if you take a look, how many
That's a
deltas
vector.
are over here in this layer? If there are 100 neurons.
100 by 1.
100 by 1, right?
That's a vector.
100 by 1. Okay.
So we just multiply.
And over here, how many deltas are here?
50.
50 by 1.
So you multiply weights times that.
So if you take a look over here, if I do weights times this, won't I get 50 by 1?
Yes.
So see, simple matrix multiplication will give us the deltas here. Same thing over here. Again, whatever the weights are, suppose we have 500 neurons over here, this will be 500 by 50 matrix. Multiply this weight matrix by the deltas and we'll get the, and then once we are in the deltas over here, multiply it with the x vector and you will get all the weights over here. So now let's develop the matrix form of our neural networks. But like I said, when we deal with very high dimensional data, we cannot be dealing with individual weights like we were doing W1, W2. I did that so that at least you know how the computations work, right? In real life, from now onwards, well, not from now, I'll give you one assignment where you'll do it individual weights, so that at least you know it works. You know, just a small 2x2 network, you'll compute the weights and the biases by expanding the partials. Okay, once you are convinced, yes, it works, then we'll deal with large networks, everything in terms of matrices. Okay, so.
What do the biases represent?
Biases represent, think of it this way, let's say the output was supposed to be 0.2. right? But for some reason, output, before we go through the activation, is coming out negative 20 for whatever reason. So if the bias is 20, it's basically, if you were from the electrical engineering background, if we have a signal, let's say a signal is like this, right? And we wanted it to be centered in the 0 point over here. We simply add a DC to it so that this gets shifted over here. So bias basically moves the curve up or down. Okay, it doesn't change the shape of the curve.
So same thing applies to the activation function as well, right?
Activation is doing a nonlinear transformation because it's limiting the output between 0 and 1 if it is sigmoid. So in a way, let's say all your data was negative 20 to negative 200 before you pass it through the activation function, right? What will be the output of the activation function? Always 0, if that was the case. But now if you can move the data up so that it varies from minus 70 to, let's say, plus 50 or whatever, right? By adding a bias, then sometimes, as you can see, output will be 1, sometimes it will be 0. Okay, so let me go 10 more minutes, explain the matrix form of our development. Then your next assignment will be dealing with matrix form, and as well as one part with individual weights and biases. So okay, so let's do this. Let's create 3 neurons. Okay, and suppose 2 inputs, x1 and x2. Or let me make it 3 inputs to make it easier for us to see, right? So all 3 will go over here, correct? Okay, what will be our terminology? What will we call those weights?
Oh, yeah.
W,
1,
1, W.
1, 2, 1.
First is the output.
So 1, 2, 1.
1, 2 of 1. So now I'll give you the motivation why I picked the output first and not the input. Okay. Then what will this be? 1. Right? Very similarly, now let's go use a different color. Okay, what would you call this?
That's 2 or 1. 2, 1 or 1.
Output 2, input 1.
2, 1 or 1.
Output 2,
2, 2 or 1.
and output 2, input 3. Output is the neuron number. See, this is 1, 2, 3. Okay, let me use a blue color over here. Can you tell me what will this W be?
3, 1.
3, 1.
And 3, 2, 1. 3, 3, 1. Elements permit this of 3 by 3.
Okay, and so on. Okay, so let me now write the expression for S1, S1 of 1, S2 of 1, S3 of 1. Okay, So according to our equation, S1 of 1 will be x1 times W11 of 1 plus x2 times W12 of 1 plus x3 times W13 of 1 plus B1 of 1. Everybody agrees? Okay, let's write the expression for S2. S2 of 1 will be, so all the red ones, right? X1 times W21 of 1 plus X2 times W22 of 1 plus W23 of 1. Sorry. X3 times W23 plus B plus B2. Everybody agrees? Okay, what will be the expression for S3? The blue part over here, x1 times W31 of 1 plus x2 times W32 of 1 plus x3 times W33 of 1. And lastly, plus 3. Okay, so can we write it in matrix form over here? Okay, so if you take a look over here, essentially S could be written as W times X, right? And what is W over here? W is W11 of 1, W12 of 1, 13 of 1, 21 of 1, 22 of 1, 23 of 1, 31 of 1, 2 of 1, 3 of 1. And the x is the vector x1, x2, x3. Okay, if you do, remember in matrix by a vector multiplication, we do row times column. So you can see this will turn out to be equal to S1 of 1, S2 of 1, S3 of 1. So in matrix form, we can simply say S equal to Wx. So on purpose, when we were indicating the weights, right, I said first will be the output number, then will be the input number. Okay, and the reason again we did that was otherwise, as you can confirm it yourself, it will not come out a clean matrix by vector multiplication. So as a result of this, it turns out nicely. So now let me show you something on my computer. I'll talk about your next assignment, and you can extend the same idea to the next layer, to the next layer. So all layers will now be connected by matrix multiplication with the previous layer.
But we also have to include the bias, right? For S as a vector.
Oh yeah, I forgot. This should be plus B. Good point. So plus B. And B is B1 of 1. And then there should be a plus 3. Okay, is everybody clear? I can erase this, right? Okay, so let me try to find it. I'm looking for. Like this one, that's old stuff. Give me one more try. I forgot where I stored it. I had it on the, it's one of the assignments from the last year, but since I removed all the assignments for the last year, so let me just describe the assignment to you.